Hello, everyone. This is our fourth lecture in the sensitivity analysis for linear program. So last time I gave you one example, and today I'm going to provide you another example. And we're going to answer for a series of questions, just like we did last time. So first, let me share my screen. Okay. Okay, so I got this example problem from the one of operations research textbook by Dr. Winston. So in this example, Zales jewelers uses rubies and sapphires to produce two different types of rings. And type 1 ring requires 2 rubies, 3 sapphires, and 1 hour of the jeweler's labor. And type 2 ring requires 3 rubies, 2 sapphires, and 2 hours of the labor hour. And excuse me, each type 1 ring can sell for $400. And each type 2 ring sells for $500. And we also assume that all of the rings produced by Zales should be sold. And as of now, Zales has 100 rubies and 120 sapphires and 70 hours of jeweler's times available. Okay. And it is known that the extra rubies can be purchased at a cost of $100 each. And the company has to produce at least 20 type 1 rings and 25 type 2 rings, okay, to meet the market demand. And we'd like to know how many of each types of rings should be produced in order to maximize the total profit. Okay, now I want you to pause the lecture video for a while and then try to think about how to formulate this problem. And then try to answer for the questions. Okay, maybe first few questions if you could, and then come back whenever you are ready. Okay. Okay, so this is the LP model. In a minute, I'm gonna just let you know how I come up with this LP formulation. And this is the Lindo input. And that's the Lindo output. Okay. Okay, so let's talk about the LP model. So let me split the window in half, and then I'm gonna use MS Word. Okay. Let me minimize this. Okay, I think this should be better. Okay. Okay, so the primary decision for this example is to know how many of each type of rings has to be produced to maximize the total profit, right? So okay, so here we define x1 variable stands for type 1 ring produced. Okay, oh, sorry, number of type 1 rings produced. And x2 stands for number of type 2 rings produced. Okay. And what else? According to the problem description here, extra rubies can be purchased, right? Because extra rubies can be purchased, we're going to define another decision variable. Let's say R stands for the number of rubies purchased. Okay, so we define these 3 decision variables. And we know that our objective is to maximize the total profit, right? So we need to consider here the selling price. What's that? Here the selling price. So we want to maximize the total profit. That's going to be using the decision variable that we just defined, 400 times x1, right? Plus 500 times x2. And because extra rubies can be purchased, the cost of $100 each using the variable R, we have to minus 100 times R, right? So that's going to be our objective function. Now we need to consider the constraint sets. So what constraint do we need to consider? I have to say the resource constraint for Ruby, Sapphire, and the labor hours, right? So here, Zales currently has only 100 rubies and 120 sapphires and 70 hours of jeweler's labor time available, right? So we need 3 constraints, 1 for each ruby, sapphire, and labor hours. And because the 2 rubies are required for type 1 ring, right? And 3 rubies are required for type 2 rings. An extra ruby can also purchased. So we have 2 x1 plus 3 x2, right? has to be less than equal to 100 that's currently available. And also extra Ruby can be purchased, right? So you have to add the extra rubies purchased. Okay, so that's the resource constraint for Ruby. Okay, so the first constraint is for the Ruby. And for the next one is Sapphire. 3 sapphires are used for type 1 ring, and then 2 sapphires used for type 2 rings, right? So that's going to be 3x1 plus 2x2, right? And only 120 sapphires are available. So it has to be less than or equal to 120. Okay. And the next constraint is for the labor hour constraint. So it's going to be x1 plus 2x2, right? Because only 1 hour is required for producing type 1 ring and 2 hours for type 2 rings, right? But there are only 70 hours available, so it has to be less than or equal to 70, okay? And what other constraint do we need? I would say the production requirement for each type rings, right? The Zales need to produce at least 20 type 1 ring and 25 type 2 rings, right? So that's going to be x1 has to be greater than or equal to 20, and x2 has to be greater than or equal to 25, okay? So these 3 constraints are resource constraint for rubies and sapphire, and this is labor hour, right? And the last 2 constraints are the production requirement for type 1 rings and type 2 rings, okay? Of course, you need to add non-negativity restrictions, both variables x1, x2. Also, the number of purchased, Ruby purchased has to be non-negative. Okay, so putting all together, this is the complete LP model. So that's why we have here, okay? And okay, so only difference is I moved R to the left-hand side, especially if you consider Lindo, then all of the decision variable has to be located in the left-hand side of each constraint, right? So in that case, you have to move this one of the decision variable R to the left-hand side. But for the lingo, you don't need to do this, okay? Okay, so this is the lingo. I'm sorry, the input for Lindo, okay? And of course, if you run this program, then you are gonna obtain these optimal solutions, okay? And in a minute, we are going to talk about reduced cost, dual prices, and slack variables, in addition to this optimal solution and optimal objective function value, right? And both Lindo and Lingo also provides these range informations, the allowable ranges for the objective coefficient and the right-hand side values of each constraint, right? And also, earlier I showed you how to obtain this final optimal table from Lindo, from classic Lindo. I don't think the Lingo can provide this information. So if you missed it, please watch the previous recordings. I believe about the sensitivity analysis, second lecture, I believe. Okay. Okay, so so this is the, okay, these are the list of questions, number 1 through 9. So that's what we are going to do for today. Okay, we are going to answer for these questions, just one by one. Okay, and let me insert blank pages so that I can use them. Okay, I think that should be enough. Okay, and okay, so the first question. Suppose instead of $100, each ruby costs $150. Would Zales still purchase rubies? Yes, no, or cannot be determined? Okay, so first, let's look at the solution value. Okay, so the optimal solution indicates the Zales has to purchase 15 rubies, right? Because the optimal solution value R has 15 to maximize their total profit of $19,000, right? So let's look at the formulation. Okay, here's our formulation. So the new objective coefficient value for the variable R right here is going to change to negative 150 from negative 100, right? So that is the decrease of 50, right? So let's look at the objective coefficient ranges, allowable ranges. So the decrease of 50 for the variable R is still within the allowable decrease limit, which is 100, right? And do you remember here the according to the Lindo output, the allowable decrease in the objective coefficient ranges for each variable is the amount by which the objective coefficient can be decreased without causing a change in the basis. So within these allowable ranges, the current basis won't change, okay? So in other words, if you look at the optimal solution, So within the allowable objective coefficient ranges, the Zales has to produce 20 type 1 rings, right, here, and 25 type 2 rings, right? And they still have to purchase 15 rubies to maximize their total profit. So my answer for the first question is yes. Zales still purchase rubies. Okay. Okay, now let's move on to question number 2. Okay, so what is the most that Zales would be willing to pay for? Another hours of jeweler's time. Okay, question mark is missing. Okay, so in this case, what information we have to look at? If you remember, door price. Okay, so door price is the amount by which the objective would be improved given a unit of increase in the right-hand side of the constraint, right? But do you remember, if you want to use the dual price, you always have to check the allowable ranges of the corresponding right-hand side values, because the dual price is valid only if the corresponding right-hand side value changes within the allowable ranges. Okay. So if you look at our formulation, so the third constraint here that actually appears in the first row in the Lindo or Lingo output, right? This constraint refers to the resource constraint for the labor hour, right? So you need to first look at the allowable ranges. For the right-hand side value for the third constraint, right? Which is this. And we are looking at this value, 3.33, right? So the increase amount of 1 is still within these allowable ranges, which means we are able to use the dual price of 200, okay, for row number 4. So this tells us that if Zales pays exactly $200 for an additional labor hour, there would be no effect on their net profit, okay? In other words, the additional profit would be exactly balanced with the additional labor cost. So the ideal answer for this question, $200, okay? from this door price. That's the $200, okay? Okay, how about next question, number 3. Okay, so so your answer in question number 2 is valid for up to how many additional hours? I believe we've already answered for this question number 3, while we are answering for the question number 2, right? So we looked at the allowable ranges for the right-hand side values, right? Because this range is the range of the feasibility, right? Within these ranges of values, the current optimal solution remains feasible, okay? In other words, within these ranges of values, the dual price remains valid. So for the row number 4, right? That's what we looked at. The allowable increase in the right-hand side range is 3.33. So we may say that for up to 3.33 hours. For up to 3.3333, okay, hours. The answer in number 2 is valid, okay? Does that make sense? Okay, now we can move to question number 4. Okay, so if the variable slack 4 were to increase by 1 hour, then according to the substitution rates, the number of rubies purchased would increase, decrease, or remains the same. Okay, so the coefficients in the optimal table is called the substitution rates, right? And we've learned that last time. If one of the non-basic variable, in this case, xj, increases, the basic variable in row number I, which is xi, will decrease at the rate of alpha ij, okay? That's how you can interpret the substitution rate. So if you go to the this one, substitution rate, and we are looking at slack 4, right? So we are looking at slack 4 column for variable r, right? So we are looking at this column, but specifically for r. So we are looking at this value, okay? So we have positive 2 as the substitution rate of slack 4 for variable r, right? So what does it mean? As slack 4 increases, the basic variable in this row, which is r, the basic variable r, is the number of rubies purchased, right? Would substitute for 2 rubies. Make sense? So the answer is decrease. Okay. Now, number 5, question number 5. If the variable slack 4 were to increase by 1 hour, then according to the substitution rates, what happened to the number of typed rings made? So again, we need to go to the final table and still looking for slack 4 column, right? This time for x2 variable. So the corresponding substitution rate is 0. Okay? This means that changes in the slack variable 4 does not have any effect on the value of the decision variable x2. Okay? That is the number of type 2 rings produced. Okay? So the answer remains the same. Okay. Now, question number 6. If the variable slack 4 were to decrease this time, decrease by 1 hour, then according to the substitution rate, what happened to the number of type 1 rings made? So again, refer to the final table, slack 4 column, this time for variable x1. So we are looking at the value of 1, okay? So this indicates that the changes in x1 variable is opposed to that of slack 4. Okay, so as slack 4 this time decrease, right? The variable x1 will increase by this much. Okay, so it's going to be increase. Okay, and how about number 7 then? If we wish to determine the effect on the above solution, if 1 additional hour of jeweler's times were available, we would increase or decrease the variable slack 4 by 1 unit. So you need to check mark whichever correct. Okay. So let's look at our constraint formulation, LP formulation. So again, the labor hour constraint is the third constraint that appears in the 4th row, the Lindo-Lingo output, right? So the constraint, let me write it down here. X1 plus 2x2, right? Is less than equals 70. That's the labor hour constraint. Right? And by introducing the slack variable, this inequality constraint becomes equation, right? So x1 plus 2x2 plus slack 4, because this constraint appears in the fourth row in the Lingo output. Although this is our third constraint, we're gonna name it 4 up here, okay? And then we're gonna have equation right now because of slack variable, okay? You remember slack variable here represents the unused amount of resources for each resource constraint, okay? Okay, now 1 additional hour of jeweler's time is available, right? So here it says if 1 additional hours of jeweler's times are available. So we're gonna add extra hour here, right? So right-hand side becomes 70 plus 1. However, we're gonna move this plus 1 to the left-hand side, okay? So we're gonna have x1 plus 2x2 plus, inside parentheses, we're gonna have slack 4, right? Minus 1 equals 70, okay? Because we move positive 1 to the left-hand side. So we're gonna have negative 1 here, okay? So this means that to determine the effect on the production plan of increasing the labor hour by 1 hour, we must decrease the slack variable, SLK4, right? Slack 4, that is the unused amount of the labor hours, from 0 to negative 1 hour, okay? Because currently the slack 4 has 0 value here. Slack 4 has 0 value in our current optimal solution, okay? So we have to decrease the slack variable, the slack 4, from 0 to negative 1 hour. So the answer is decrease the variable slack 4 by 1 unit. Okay. Okay, then so question 8, right? Okay, suppose that instead of $500, each type 2 ring were to have a profit of 400 each. Would Zales reduce the number of such rings produced? So this change means a decrease of 100 in the objective coefficient of the variable x2, right? So again, the Lindo output, according to the Lindo output, the objective coefficient ranges is the amount by which the objective coefficient can be either decreased or increased without causing any changes in the basis, in the current basic solution, okay? So let's look at the objective coefficient ranges, allowable ranges. Okay, right here. So the allowable decrease of x2 is infinity. This means that the basis is unchanged for any decrease in the objective coefficient of variable x2. And this seems intuitive because we all know that the current optimal solution indicates that Zales has to produce no more than the minimum numbers required for each types of rings, right? Here, the optimal solution currently suggests to produce 20 type 1 rings and 25 type 2 rings. And here, the constraint, the production requirement constraint for type 1 and type 2, each are x1 has to be greater than equal to 20, x2 has to be greater than equal to 25, right? So a decrease in profit would obviously not make it more attractive to produce these rings. So the answer is definitely no. Okay. Okay, then let's talk about the last question for today. Question number 9. Okay, so suppose that instead of $500, each type 2 ring were to have a profit of $600 each. Would Zales increase the number of such rings produced? Yes or no? Or cannot be determined? So the objective coefficient of the variable x2 has been increased by 100, right? So again, if you look at the formulation, the new objective coefficient value for variable x2 is going to change from 500 to 600, right? That is an increase of 100. So we need to look at the allowable ranges for the objective coefficients, which is still within the allowable increase in the objective coefficient ranges, right? Which is 200. Is that correct? So within these allowable ranges, if you remember, the current basis remains the same, okay? In other words, within these allowable ranges, the Zales has to produce 20 type 1 rings and 25 type 2 rings, and also purchase 15 rubies, okay? So the answer is no. Zales would not increase the number of type 2 rings produced, okay? Okay, so this is all for today. And next time, I'm gonna give you another real world examples. So hopefully you will have better idea, okay, after you watch the my lectures. And as always, if you do have any questions or concerns regarding my course materials, then please reach out to me. Feel free to reach out to me. Okay, thank you. Okay, bye-bye.